All right. So, Jimmy has, of course, brought that bottle of stuff that he found in his fridge and decided not to eat because of it was not the milk that he had hoped it was. He decided to bring it to his round of newsboy friends. So, and since, this is, it's cold and everything, they have decided to see if this stuff burns, and boy, howdy does it burn great, okay? So, the material it combusts, reacts with oxygen from the air, and produces carbon dioxide and water, okay? Those types of organic compounds, hydrocarbons, have carbon, hydrogen, some oxygen. They burn, which is react with oxygen from the air, to produce carbon dioxide and water. Now, of course, we all know that the carbon dioxide is of particular concern these days, and of course the newsboys are very concerned about the future. So the question is, how much carbon dioxide does it give off? Different compounds will react, right, to differing amounts. It really depends on a lot of factors about the compound, in particular its chemical structure. How, Jimmy wonders, does this stuff react with the oxygen? What is the ratio? How much oxygen is being used up? How much carbon dioxide is being produced? Okay? We want to talk about chemical reactions. How can we represent the reactivity, the reaction between the ethanol, right, and the oxygen from the air? And there's a couple parts of this. One is we want to be able to do some math with these things. And the second is we want to be able to write down symbolically what's happening. We can say in words, ethanol reacts with oxygen to produce carbon dioxide and water. We can take those words, but we want to be able to take those words and convert them into a chemical equation. And we do that first by converting the words for an individual molecule into its formula. To convert the words into a chemical formula, we put the formulas together to create an equation. Okay? So, chemical equations are like the sentences of chemical reactions. If I say the words, ethanol reacts with oxygen gas to produce carbon dioxide and water, we all have a sense of what that is. We all know, or should be able to convert these words into formulas. What is the chemical formula for ethanol? C2H5OH, or C2H6O, right? We've seen it either way, but C2H5OH. So when you see the word ethanol in here, you're going to literally convert that into a chemical formula. Now we have the word, or words, reacts with. How symbolically could we represent something reacting with something else? We could use a plus sign. That's like mathematically means they're adding together. Okay? So, ethanol reacts with oxygen gas. What's the formula for oxygen gas? Remember the Hahn-Fickelber's diatomic molecules? It is O2. So oxygen gas is O2. Well, the Hahn-Fickelber's are what we call the diatomic gases. So all those compounds are gases, sort of. Diatomic molecules is probably better. To produce, to form, to make. Okay? Now in math we would think equals, but we're not in math class. So to produce in our case is going to be indicated by an arrow. We use an arrow to indicate to produce, to form, to make, to synthesize. Those are all words that mean the same thing. This stuff reacts to make this other stuff. So carbon dioxide, CO2, and what am I going to put for the end? It's a plus, water. So here is our sentence. We have our reactants on the left. We have our products on the right. Okay? And so we have a chemical sentence, a chemical equation. Okay? So, Jimmy's naive friend Billy, of course, feels that this clearly shows us that we're going to get 1 carbon dioxide when we burn 1 ethanol. Okay? Is Billy correct? Is that the way that this works? What do we have to worry about? Do you see the subscript, right? The subscript 2 here? Right? That's 2 carbons. This equation is not balanced. Okay? We have to make sure that all the atoms that show up on the left-hand side also show up on the right-hand side. We can't have atoms appear or disappear. They can't, all the atoms have to be the exact same. How many of each element has to be the exact same on each side. We are not dealing with nuclear reactions. In nuclear reactions, you can have changes. Atoms change from one type of atom to another. They change what element they are. We're not going to do any of that kind of stuff for now. Okay? So what we want to do is we want to go back to look at our chemical equation and say, all right, this equation is not balanced. What could I do to balance this equation? What things could I start to change? I need to add molecules, right? I need to add. But now, do I want to put in some other, like can I add some carbons over here? No. That would change the sentence. And I don't want to change the sentence. What I want to do is I want to correctly represent what's happening. Right. So, exactly right. We want to put some numbers in the front of each one of these guys here. We want to say how many carbon dioxides are made, how many waters are made. If I change the, if I add some extra elements or extra molecules, that's changing what the chemical reaction that's taking place is. If I change the subscripts, that's changing what the molecule is. I can't change and put a 2 in subscript 2 here. That would change what the molecule is, and then it doesn't match the words that we were given. Okay? When you are balancing, the only thing that you can change is the coefficient, the number that you write, the big full-size number that you write in front of a molecule to indicate how many are there. For every X one of these guys, how many of these guys do I have to have? And what I would say, the way to do this is to look for elements that only occur in 1 molecule on each side. That's the first thing to start to balance. If I try to look at the oxygens, oxygens occur in every single molecule. It's going to be really hard to try and figure out how many there are. Carbon, on the other hand, only exists in the ethanol and the carbon dioxide. So I know that if I have 2 carbons here, what do I have to put in front of the carbon dioxide to indicate that I have 2 carbons? And I have to put the 2. I got to balance it by adding coefficients. What this says is that I have 2 carbon dioxide molecules. Okay, I have 2 carbon dioxide molecules. They're separate. They're not bonded together. They're 2 separate carbon dioxide molecules. Each one has 1 carbon in it, so altogether there are 2 carbons. 2 carbons on the left, 2 carbons on the right. Carbons are balanced. Other stuff is not yet balanced. Okay, other stuff is not yet balanced. How many hydrogens do I have on the left-hand side? I got the 5 and the 1 more, that's 6. How many hydrogens do I have on the right-hand side? 2. How can I make those balance out? 3. I need to put another coefficient. I need to put a 3. 3 times 2 is 6. That means I have 3 water molecules, 3 separate water molecules. Each one has 2 hydrogens. So now I've balanced the carbons and the hydrogens. The last thing I have to balance is the oxygens, right? So what I need to do is I need to go through here and figure out how many oxygens do I need, okay? How many oxygens do I need? That's the last thing. Now it occurs all over the place. So I got to look at the oxygens and say, all right, I got 1 oxygen here, and I have 2 more, but when I see an element by itself, I know I want to save that for last. Because if I change the coefficient on this oxygen, it doesn't change anything else. If I change the coefficient over here, it's going to change the carbons and the hydrogens, messing up all the work I just did. So when you see an element by itself, save that one for last. Okay? So I got 1 here I have to remember. How many oxygens do I have on the right-hand side? 2 times 4, or 2 times 2 is 4. 3 times 1, so I have a total of 7 oxygens on the right-hand side. The coefficient multiplies through all of the subscripts. The coefficient multiplies all of the subscripts. Okay, because what it's saying is, hey, I've got a CO2 molecule and another CO2 molecule. I've got 7 over here. Okay, that gives me 1. So what do I got to put here to make this work? I got to put a 3. Okay? That's balancing chemical reactions. Look for elements that occur in one molecule on each side. Start with those ones. If you have any element by itself, save it for last. Okay, save it for last. And then it's an iterative process of, okay, 2, 2, 2, 2. Sometimes you're going to have to come back and you'll say, oh, I had to change this number, which means I got to come back and change all these numbers. There's a certain amount of guess and check involved. It's an iterative, cyclical process. Okay? So once again, Billy says, great, no worries. We get 2 carbon dioxides for each ethanol molecule we burn. So if I burn 1 ethanol molecule, I'm going to use up 3 oxygen molecules and make 2 carbon dioxide molecules and 3 waters. What if I burned 1 mole of ethanol? How many moles of oxygen would I need? 3. How many moles of carbon dioxide? And how many moles of water? Remember, a mole is just a certain number. So if it's a 1 to 3 to 2 to 3 ratio, that's the ratio of numbers of atoms or molecules. So it's the same exact ratio of the moles. 1 mole, 1 atom, 1 molecule, 3 molecules, 2 molecules, 2 moles, 3 molecules, 3 moles. Same ratio, because moles is just a big number. Okay? Example problem. What if I told you that milk sugar, galactose, C6H12O6, burns in oxygen to produce carbon dioxide and water? Write a balanced chemical equation showing that reaction. What do you need to write down first? What's the first step in writing a balanced chemical reaction? Convert all of these words into the basic what molecules exist. Okay? Then you can go through and start to try and balance. Give it a shot. All right, did you convert the words, right? Step 1, convert those words. I gave you the galactose, that's nice of me. Oxygen, remember diatomic, O2, carbon dioxide, and water. Should I start balancing with the oxygens? Would that make sense? Do, do, do. What should I start with? Carbon or hydrogen. Carbon or hydrogen would be my best bet. I've got 6 carbons over here. What do I got to do to this?
6.
I've got how many? 12, which means I better put a 6. Then I got to come back. There you go. C6H12O6, 6 O2s, 6 CO2s, 6 H2Os. Yeah, yeah, it was when I started writing these, I thought it would be fun to put those in. Okay, so we can see that when I burn 1 molecule of galactose, I get 6 molecules of carbon dioxide. Well, burning is it turns out that you can have burning reactions like with nitrogen. You're going to get compounds to react.
Why would you say burning in oxygen and not burning with
Typically, that's just the way it's frequently phrased. Burning in an oxygen atmosphere.
Would burning be exothermic or?
Burning is typically exothermic, and we'll get there. So questions? Huh? Moose is still eating the milk that they found. They're not eating moose for dinner. So, ethanol only produces 2 carbon dioxides, while galactose sugar makes 6 if you're going to burn them. Okay? But is that really the best way to gauge these things? This is a per molecule basis. Okay? But there are other considerations we might want to think about tomorrow at Tara. All right.